Welcome to this explainer. I always like to think of chemistry not just as a science, but really as the ultimate detective story. All around us, atoms and molecules are constantly interacting, transforming, and basically hiding their true identities right in plain sight. Every single chemical reaction, it's essentially a crime scene left behind by these microscopic actors, and the formulas and equations, well, those are our clues. Today, we're going to learn exactly how to read those clues. We're stepping into the shoes of a chemical detective to uncover hidden molecular identities, track down missing masses, and finally crack the chemistry code once and for all.
Okay, let's dive right into this. Here's our roadmap for today's investigation. First, we'll be classifying our material world. Then, we'll meet the mighty mole. Next, we cover the unbreakable laws of chemistry before solving some stoichiometry mysteries, and finally, cracking the chemical formula itself.
So, let's start with part 1, classifying our material world and setting the scene.
You see, the entire chemical universe is broadly divided into two main camps: pure substances and mixtures. Pure substances, they have a constant, unwavering composition. Whether it's an element made of just one type of atom, like the oxygen gas we're breathing right now, or a compound like water, they always follow a strict recipe. Mixtures, on the flip side, have a totally variable composition. You can have a homogeneous mixture where everything is blended uniformly, kind of like the air in the room you're sitting in, or you can have a heterogeneous mixture where the components are distinct and visible. Think of a mix of salt and sugar or dirt and rocks. Knowing whether you're dealing with a pure substance or a mixture, that is literally step 1 in any chemical investigation.
Moving on to part 2, meet the mighty mole, the language of matter. Now, that chemical language relies on one absolutely massive number, 6.022 times 10 to the 23rd power, Avogadro's number. I know, it looks super intimidating, but honestly, just think about it exactly like the word dozen. When I say a dozen, you immediately know I mean 12. It could be 12 eggs, 12 cars, 12 stars, it doesn't matter. Well, in chemistry, atoms are so unimaginably small that counting them by the dozen is completely useless. So instead, we use the mole. 1 mole simply means 6.022 times 10 to the 23rd particles. That's it, it's just a counting unit. But it is the vital bridge between the invisible atomic world and the tangible physical amounts of powder or liquid we can actually weigh out on a scale.
Now, what's really interesting about this is that depending entirely on the clues we're handed at the scene, we have 3 primary forensic tools to find the mole. If you're given a raw count of particles, well, you simply divide that by Avogadro's number. If you're handed a physical pile of powder along with its weight, you just divide that given weight by its atomic or molecular weight to get your moles. And what if your suspect is a gas? You obviously can't easily weigh it, but you can measure its pressure, volume, and temperature. Then you just use the ideal gas equation, PV equals nRT, and isolate N, which is your number of moles. 3 totally different paths, but they all lead us to the exact same crucial piece of information.
All right, part 3, the laws of chemistry, the unbreakable rules.
This right here is the absolute foundation. Antoine Lavoisier's law of conservation of mass. In our chemistry detective story, this is the very first unbreakable rule. Matter never just disappears without a trace. Ever. If you start a reaction with exactly 18 grams of reactants, you must end up with exactly 18 grams of products. Now, the atoms might rearrange themselves, they might swap partners, or they might even turn from a solid into a completely invisible gas, but their total mass remains perfectly conserved. So the really crucial takeaway here is, if your mass after a reaction suddenly seems lower, well, a gas probably escaped.
Next up, we have the law of constant proportion, courtesy of Proust. This law essentially tells us that chemical compounds have a strict, unchanging identity. Let's take water, H2O, for example. In water, hydrogen and oxygen always combine in a fixed 2-to-1 molar ratio. And it completely does not matter if that water came out of your kitchen tap, a raging river, the middle of the ocean, or if it was produced artificially in a lab reaction somewhere. That chemical composition is rigid and completely constant.
And Dalton's law of multiple proportions takes this a step further. Because what happens when 2 elements can actually combine to form more than one type of compound? Think about carbon and oxygen. They can pair up to form carbon monoxide, CO, or carbon dioxide, CO2. Well, Dalton noticed something really beautiful here. If you keep the mass of carbon completely constant at exactly 12 grams, it'll combine with 16 grams of oxygen to make CO and 32 grams of oxygen to make CO2. If you compare those masses of oxygen, 16 to 32, that simplifies down to a perfect 1-to-2 ratio. It just goes to show, nature really loves simple whole numbers.
Which brings us to part 4, solving stoichiometry mysteries.
Welcome to the real climax of this explainer, and basically the crime scene itself, a live chemical reaction. We call this stoichiometry. This is where we take all those rules we just learned and use them to rigorously track every single reactant as it transforms into a product. But here's the catch. In almost every reaction, things don't perfectly match up. You rarely have the exact perfect amounts of every single ingredient. One of those ingredients is going to run out first. We call this the limiting reagent. You can think of it as our prime suspect that bottlenecks and completely halts the entire chemical reaction. It's like if you're building bicycles and you have 100 frames but only 4 wheels, you can only build 2 bikes. The wheels are your limiting reagent. But in a complex chemical soup, how do we actually identify which chemical is the wheels?
Well, it's actually a highly logical, foolproof, two-step process. Step 1, you take the given number of moles of each reactant that you've already calculated, and you divide it by its respective stoichiometric coefficient. That's the big number balancing the chemical equation. Step 2, you just look at the results. Whichever division comes out to be the absolute minimum value, that reactant right there is your limiting reagent. And once you identify it, every single other calculation for the products formed has to be based entirely on that limiting reagent, because the second it's gone, the reaction is completely over.
But wait, what if you don't have a perfectly balanced chemical equation? What if the reaction is so incredibly complex, or maybe it goes through so many sequential steps that balancing it is nearly impossible? Well, enter the principle of atom conservation, or POAC. This is essentially a brilliant cheat code. It simply states that if atoms are conserved, which we absolutely know they are thanks to Lavoisier, then the total moles of those atoms must also be conserved from the very start of the reaction all the way to the very end. Meaning, you can equate the moles of a specific atom in the reactant directly to the moles of that same atom in the final product. It completely bypasses the need for a balanced intermediate equation. Seriously, it's a massive shortcut for the smart chemical detective.
Finally, we arrive at part 5, cracking the chemical formula.
Now we move into the final resolution phase. We've gathered all the evidence, we've done the tracking, and now we actually have to translate our raw percentage-based data into the exact molecular identity of an unknown compound. Let's crack the code. And this brilliantly illustrates the whole process. We start with raw percentages of carbon, hydrogen, and oxygen in some unknown organic substance. First, we just divide each percentage by the element's atomic mass, so that's 12 for carbon, 1 for hydrogen, and 16 for oxygen. This gives us the relative number of atoms, or our moles. Then, we divide all of those answers by the smallest result we got, which in this case is 3.389. That gives us a super simple ratio, 1 carbon to 1.5 hydrogen to 1 oxygen. But obviously we can't have half an atom, right? So we just multiply the whole thing by 2 to get clean whole numbers, 2, 3, and 2. And just like that, raw percentages magically distill down into an empirical formula, C2H3O2. The cipher's totally broken.
Of course, to go from that simplified empirical formula to the true final molecular formula, we still need the total molecular mass of the substance. And we ground all this theoretical math in reality by using brilliant experimental setups, like the Victor-Meyer tube. This is specifically used for volatile substances. We take a known mass of our mystery substance, drop it straight into the heated tube, and as it vaporizes, it pushes out, or physically displaces, an exact volume of moist air into a graduated tube. By carefully measuring that displaced volume, along with the room's temperature and atmospheric pressure, we can calculate the exact molecular mass of our mystery vapor. It's physical, irrefutable evidence in action.
So we've gone all the way from the big picture of pure substances and mixtures down to the mighty mole. We've tracked the conservation of mass, hunted down the limiting reagent, and mathematically decoded an empirical formula. Now that you possess these fundamental, unbreakable tools to track atoms and decode formulas, the whole molecular world is wide open to you. So my question is, what complex chemical mystery will you solve next? Thanks so much for joining me on this explainer, and keep questioning the chemistry around you.